Mm. Yeah, hello everyone. This is Vishal. Are you able to hear me? Can somebody speak out? Can somebody unmute yourself? Hello. Are you able to hear me?
Yes, sir, you're audible.
Okay. So have you went through the lectures of ninth week?
Yes, sir.
Okay. So I guess this week will not come in the second quiz, but you need to complete that I guess before 3rd of July, right? Maybe that will extend, but I don't know whether to extend or not. But yeah, so one thing is, today we'll discuss just the brief about the ninth content, and then so do you need any other sessions from fifth to eighth week in this week or maybe in the next upcoming week regarding solving questions or anything like that? Because one session will be there that will be revision session. Other than that, if you need, you can tell today.
So for week 9,
Not for week 9. Week 9 will cover this weekend, today, and then one session will be there in the Saturday. Regarding fifth to eighth week, in spite of a revision session, like one revision session will be there, but mostly the conceptual part will be covered in that. So I'm asking, do you need any other sessions other than that? Like any sessions that includes practicing of questions or anything from fifth to eighth week?
yes, sir, like an additional session for the portions that are like exclusively for the quiz.
Yeah, yeah. Yeah, that is what I'm asking. Any extra sessions from?
Yes, sir. We require,
Yes,
sir.
sir. Yeah, it would be very useful if you have.
Okay, so mostly you're facing issue in which week?
Yes, sir. Week 5.
Okay, so that is pretty fast, right?
Okay.
Okay. And one
Uh,
more thing, like in the seventh week, I told you in the last session also there is an error in the tutorial. So whoever has recorded last time, that I'm not able to remove that. Like maybe in the next time I'll remove and maybe record again. So there is an error in that, that the eigenvalues that has been calculated has been incorrectly calculated.
Yes.
Okay. So many of you have been asking. I told you in the last session also that there is an error here. I told you the procedure also how to compute the eigenvalues and all. So that is an error. So I'll again post it on the discourse also. I already answered so many times, but I'll post it on the discourse also about that, because that error is in the lectures itself. So it's very like difficult to correct in the lectures itself. So we were planning to record that, but we didn't record it. So maybe next time we'll record. Other than that, there is no error, I guess. Right?
Yes, sir. That is pretty much.
Okay. Anything else?
so syllabus is fifth week to eighth week.
Yeah, only fifth to eighth. Maybe you can get some questions that will include some conceptual part from third or fourth, because the eigen values and all has been discussed in third or fourth week also.
Okay.
But most of the question, almost all the questions are from fifth to eighth week. Maybe some question will be there where you need to calculate the eigen values and eigen vectors. Those
Okay.
include the concept of third or fourth week, but that has discussed in the I guess fifth week also. So yeah.
Okay.
So okay. Anything else? Shall we start? So how many of you have seen the lectures
ஓ
of
நம்ம
the
ஆனா
ninth
6
week?
மாசம் ஆகும் சொல்றது அப்ப 2-3 மாசம்னா கண்டிப்பா 6 மாசம் ஆயிரும் இல்லையா இல்லையா 6 மாசம் ஆயிரும்.
Okay. So how many of you have seen the lectures? Like, can you raise your hand? Only one guy has seen the lecture. Okay. Uh, so only one person has seen the lectures of ninth week. So what to do? Shall we discuss or what? Like, do you need some more time or what?
So we can just go over it. Like,
Because I guess only you have seen the lectures. That's why I shifted the session from Monday to Wednesday so that I was pretty sure, because on the Monday it's really difficult to watch the video because you have already submitted the grade assignment on Sunday itself. That's why I shifted it to Wednesday. This was the like last week of the quiz, so that I was perhaps knowing most of you will not see the lecture. So what should I do? Like, should I go through that or should I go to the last week or maybe the earlier weeks and all? What should I do?
so week 10 is pretty, like, concept-wise, it's pretty short, right?
Yeah. Mostly we
So,
have just discussed about the convex set, convex function, and then how to solve the
yeah,
constant
yeah.
optimization.
So there are only like you talk about convexity, then that approximation, the linear approximation, and you're talking about the Taylor method and this one greatest descent method, right?
So
Those
that
are
was in
pretty.
the last week, I guess. Taylor's method. So
Yeah, yeah.
the last
Okay,
week
yeah,
was almost about how to solve the optimization problem that doesn't have any constraint. This week we are
yeah,
just going to the
yeah. We are talking about constraint
constant
and
optimization. That's
yeah,
it. And mostly we are discussing about the convex function and all that.
the
That can
the
be related.
Lagrange method.
Yeah, Lagrange method, and then yeah, for the inequality we are using Lagrange, but that is also not that correct. So we'll go through that projected the gradient descent to solve the problem, and then we'll
Yeah.
see what are the. So now what to do? Whether if
So
you have
I
not
think
seen, I guess most of you will not understand the concept because the I guess the lectures are very beautiful. Like if you watch, there won't be. I don't think so. When you feel you have any issues, but you have not seen that the lectures and the. So what's the reason? Like why you already have 3 days? Maybe because of the quiz or what? And the participant is also very less. We are only 24 people. So
might be because of the quiz, sir. Like it was like there was a general notion that quiz 2 will be harder than quiz 1.
yeah, so quiz 2 is harder than quiz 1. That I can assure you. Like I have also seen the question. So it's pretty difficult.
So like we just have a brief overview on like what are the main things in like a summary so that those who have not seen the
Okay.
videos might have some ideas.
Yeah, so I'll just go through that. And about the quiz 2, I'll just tell you quiz 2, this 5, 6, 7, 8 is coming. Okay. So
Yes, sir,
conceptually,
yes.
there is not much in 8th week, but practice some questions. Okay. So conceptually, this is not that the concepts are not that heavy in 8th week. Okay, but please practice some questions. Maybe practice whatever I'm telling you. Please do that. Otherwise, you'll have problem in the exam. Seriously, for this quiz. Okay. So please practice the last term. If you're having last term question, please practice that. You can practice the graded once again. You can do that. Graded some questions, maybe the last 3, 4 that you can practice. And please do the mock. Whatever the mock will release, practice that for the 8th week. For the 7th week, it's PCA, right? So 7th week, what you can do is practice the graded itself, graded and practice twice. Maybe there are only 5 or 6 questions. Okay, so you can practice twice. right? There is only one type of question that can be made from the PCA, and so you can practice that question. So if you are having some data set, how to calculate the projected data set, how to calculate the covariance matrix. Okay, those sort of questions can be asked. We can't ask a bigger question because that will become very complex to calculate. So it would be a simpler one. So from 7th week, we can expect the simple question, but that will also be having some computation. Okay? So you can't. So only the 7th week will be having a pretty simple question, and that also you can't lose with the because of the calculation mistakes and all. Okay, so please don't do the mistakes from at least if you are getting some simple question, don't do any calculation mistakes from the 7th week. You can practice a graded maybe once or twice. Okay. That is enough. 6th week is totally HVD, so you should be knowing how to calculate the HVD. Like if you are getting the question like option form, so you can solve. But if you are not getting the options form and you have been asked to write the summation of element and all, so then it will become difficult. So it's better to practice some 1 or 2 questions to know how to calculate the HVD of any matrix. That's the one. And the other thing is so yeah, so HVD, and the other concept is regarding the definiteness of the matrix. Okay, so if you are having, so from this you can have some matrix also. For that matrix, you can be asked to tell about the nature of the matrix, or you can be given some function also. From that function, if you are able to know the matrix, like the options will be there, or if the options are not there, you can go with the Hessian matrix also. So the answer, whatever you will get with the Hessian, will be also correct. Okay. So and the some properties that we have discussed in the regarding the positive definiteness and all, like for example, if SS is a like the difficult part from this 6 week can be, so there are more sort of MSQ question in this system. Okay, so MSQ question can give you pain. Okay, so that's why I'm telling you. It's like, for example, I'm telling you, if S is a positive definite, but then the inverse of S is also positive definite. So whether its statement is correct or incorrect, those of question can be come. So maybe a bit conceptual from this 6 week. Okay, so SPD and this, then you can practice, or you can practice some SPD question, and then the regarding the nature of the matrix. There are some like 5-6 properties that is there for the matrices to know regarding the definition and all. Fifth week is what is that in the okay? Fifth week is like diagonalization and all those aspects are there, right? So from there also you can expect some MSQ questions where the mostly the statement type question can be there. Okay, so this is what I have explained, like from the aspect, the quiz paper, what I got, I just told you. So you can practice these things and maybe it will help you a bit. Any questions from here?
No, sir. These are basically the main like portions that are like give a bit more focus on those portions. Right?
Yeah, so this you can practice. Yeah. So let's move to the 9th week. So you'll be having the last term paper, right?
The previous, yes, sir.
Yeah. Last term paper you'll be having, right?
Yes, yes.
Oh. One. So last term paper, I'm okay. So if somebody is having, you can share on the Discord. Otherwise, I'll share it on the Discord. Okay. So this is the 9th week. So in 8 weeks, we have just seen how to solve any optimization problem. Like for example, if you are given to solve to calculate the minimum value of x where the function is minimum, right? So, but yeah, so we solved those sort of problems with the help of gradient. We didn't solve, we came to know what's the procedure that can be preferred if we don't have any constant issues and all. So if we have not any constant issue, you can solve the problem with the help of gradientation. There are other methods also, but the gradientation is the basic and the most important, you can say, the algorithm that we generally follow to solve any if you, like any function without any function. So this was there in the 8th week, and we have seen like in a broad aspect in the 8th week. Now we have to solve the problem. If we already have the optimization problem, so we have the optimization problem. Like for example, this is the optimization problem. Then there is some function of x, which we need to know regarding the x.
So
That's that. Yeah.
now are you sharing your screen?
Oh, you're not able to see. Oh, sorry. Oh, so week 9, lecture 1. So earlier in week 8, we have just discussed how to solve the optimization problem if you don't have any constant issue. Now in this week, we'll just solve the optimization problem with some constant issue. Like for example, this is the constant. Or you can say the condition that you need to fulfill while solving this problem. So that we have seen in the in PCA when we were going through the proof of the PCA. So we were having some conditions, right? And we were able, like we were asked to solve some optimization problem in the PCA, and we were given this. And at that time, our constant was what? Can somebody tell me what was the constant while solving the PCA problem? So while solving the optimization problem of the PCA, what was the conditions that we were talking about the vector, right? So vector, the optimization problem was what? We were finding the vector, the direction of the vector where the variance is maximum or the construction error is minimum. But with that, we were also applying some constant, right? And what was the constant that we were applying on that vector? So that, okay. Can anyone, are you able to see the screen right now?
Yes, we can see.
Okay. So yeah, so tell me what was the constant at that time when we were solving the optimization problem of the piece?
Is it the loss?
No. So that no, not loss. That optimization problem that we were applying was this one, right? So the vector was unique vector, right?
Ah, yes, okay, yeah.
Yeah. So
When
this was
we
the
take the yeah.
Yeah. So this was the constant that we were applying while solving the piece, and then we solved with the help of Lagrange multiplier. So okay, that is different. Just I was like recalling the constant. So now everyone would be clear. This is the optimization problem, or this is our objective. This is our condition or the constant that we need to apply while solving this question, while solving this problem. Okay. So yeah. So what are the main conditions? Like if somebody of you has told, okay, I got the x, and that x is the x star that is satisfying this equation. So that x star is satisfying the condition. So what are the important conditions or the necessary things that we should be seeing? So the first thing, if somebody is claiming that x star or x bar, whatever you can assume, is the solution for this optimization problem. Okay. So the first thing that should satisfy is what? that if I'm putting G star in this constant function, so this X star should be less than equals to 0, right? And the other thing that maybe you have not seen the lecture, so you'll get a bit difficulty here, but it's fine. I'll just try to explain that. There should not be any decision direction. There should not be any decision direction. That is feasible direction. What does this mean?
There should not be a lower. There should not be any lower f of x star that is greater than g of x star that is within that is greater than 0, that is within the points that we selected.
Yeah. So one thing, okay. So one thing is what is feasible direction. The feasible direction you already know, right? This is a property of that G star, right? This is a property of G. And this is the properties of F. That in the when you were solving the problem, optimization problem, where there was there was not any constant. Where also we used to talk about the decision direction, right? That del of F we were calculating, right? And that should be negative. That we were discussing in the last week. So there should not be any decision direction that is feasible also. That means if you are able to find any like what we are doing here, we are just trying to know whether F star is a solution for this equation or not. So if somebody has claimed that the F star is a solution for this equation, now we are checking. So what we have done first, so we have first checked whether this satisfying our constant or not. So okay, satisfied. Like there can be X star that generally satisfied our constant, but it doesn't satisfy the other conditions also. Like there can be like X value, right? So our first equation was satisfied, but the second equation that we need to check is we should not be having any decent function that is also feasible direction, like the decent direction that is not. That means like there should not be any direction, like whatever you're getting. If you are able to, like for example, if I'm able to get any direction where from where if I'm moving from X star, if I'm moving and I'm getting some values which is lesser than X star. So that means what? X star is not the minimum value, right? There should be other X, there should be some other X value where the function will be minimum, right? If I'm able to get some direction where if I'm moving and that's satisfied our constant also because that is satisfying already, and if I'm able to get the minimum or if I'm able to get the values which are basically minimum or lesser than the function of the function of that value at X star. Like for example, if earlier this was a function and I was claiming this was the X star, I was claiming that this is the X star, right? So there is a direction, right, where I can move, and there we can move and we can get the value which are lesser than this function. Like here the function values are what? The function value is X star, but we can get some if this X we can get this was X star and this X transpose like xt or what x1 I can. This is some other value, this is x1. We can claim, we can say now we are able to get some different direction. This is feasible also. I'm able to get x1 also where the values of the function value is lesser than x star, like x star, right? We can say that. So if I'm able to get any such direction, then we can directly say this is not the optimum value, that is x star, that we were claiming that this is the x star, that is the final answer. Okay, that is the solution for this optimization problem, right? So till now it's clear, right?
Yes, sir.
So we should not be getting any. So there should not. So the first condition is that G star the constant should like if somebody is claiming X star is a solution, then it should satisfy both the conditions. First is is to satisfy the constant, and the second is there should not be any decision direction where that is feasible direction also. Okay, and the feasible is the simple property of Gx, and the decision direction is the property of X or the optimization problem in which we are applying. Okay, so this was there in the lecture one, and what else was there? Okay, so now we'll move to the direction. Okay, so like for example, I'm having, so we need to find, there should not be, if there is any, like for example, if this is the function, and if there is a optimization function of X, so this is the direction of the gradient. This is the direction of this gradient. Right? So which are the area where we can get the vector when we'll apply the dot product with this del of fx, we'll get negative value. So which are simply the areas where we'll get the negative value?
That's
This area, right?
yes.
So this is the area. Like simply this all this area. So here we can get some vectors. All the vectors, it will do the dot product with this gradient of this x star will get the negative value. Right. Now, for example, this is our this gradient as x star. We can have the gradient of g star also. This is the direction of the gradient of g star. Okay. So, okay. So for this, the perpendicular thing would be this one. Now, what is the common area? Like the area where what are the vectors? What are the places where if you multiply the c? So the first thing was this area. So this area will give us the vectors or the direction of the vectors, which are decision direction, right? And for the feasible direction or the property like where the g star is less than equals to 0, that can this area would be that, right? Where if we are multiplying, if we are taking the dot product with the gradient of g at x star, so we'll be having this area, right?
Yes.
So if like for example, that g star, we were claiming that g star was the solution for that optimization problem, right? But for the g star, so this thing was applicable, but when we were like applying some basic concept and we were trying to know whether we are able to find some direction that is feasible also, so we were able to know that. So there are many, right? So this is the common area. This is a common area for feasible, and this is a common area for the decision. So now we are having this area, total area, right? Where you can find that there are the vectors which are applicable, which are giving the negative when we are doing the dot product with the gradient of f also, and we are having in the same area we are having the vectors which are giving the dot product when we are doing the dot product with the gradient decision gradient of the gx star, that is also negative, right? So we are able to find so many vectors, right? But what we were like, we should not be having any of them. If we are able to know there is not a single direction that is feasible, like there is not even a single decent direction that is feasible, then only we'll be able to say that okay, this x star is the function, or x star is the solution for our optimization problem. But in this case, when the direction of the gradient is here and the direction of the gradient of the g star is this way, in this direction, now in this case we can directly say this x star is not the optimal value for which we are solving the optimization problem, correct? Or
Yes.
any issue in this? you don't have any issue, right? So now, so I guess this was there in the lecture 1. Now we'll move to the lecture 2. So mostly in the lecture 2 now, we'll see that in the lecture 1 we have discussed about the basic concept. If somebody is claiming that X star is the solution for the optimization problem, what are the basic necessities that should fulfill? Okay, so we just came to know there are 2 basic necessities that should fulfill. The first is that it should satisfy the constant issue, and the second is there should not be any decision direction that is feasible. Okay, right. So now it's like, for example, okay, so one more example. If I'm having, so can somebody reply on this? If I'm having this is the direction of fx star, and the direction of this gradient of this is also same. Can somebody tell me? And if this is satisfying the first condition, so this is X star here, whatever I'm taking this X star is satisfying our first condition, like for the constant thing, like if I'm writing this is satisfying our first condition. So can somebody tell me whether it's satisfying the second condition or not? If the direction of the gradient is like both are parallel to each other, the gradient of F and the gradient of G. Can somebody tell me whether it's satisfying the condition for the second one or not? The second one is whether we are able to find any vectors that is whether we are able to find any direction that is optimal. Sorry, that is decision direction also, and that is feasible direction also.
Yes, sir.
Yes. Okay.
So
How
the whole thing will be like below the light to the left of the line.
Yeah.
Will be
So
feasible distance.
Yeah, correct. So this is the decision direction for F also, and the same area will be the decision of the feasible direction for G also, right? So now we were just searching for if we have to claim that X star is the solution, so we should not be not even a single direction. But here what we are getting a hell lot of values, right? We are having a lot like infinite number of direction where the infinite number of direction that is a decision direction, and that is feasible. Okay, so this X star is also not our optimum solution, because this is satisfying the first condition, but it's not satisfying the second condition, right? So now if I'm having this type of equation, right, and this is the and this is the okay. So now can somebody tell me whether can somebody tell me whether this is satisfying our condition, the direction of this FP?
No.
So for this X star, our first condition I already know this is satisfying. So G. Okay. You can tell me whether are you able to find any optimum? Are you able to find any direction, any like what do you say, the decision direction that is feasible also? Are you able to get any direction? If I'm having if both the vector are anti-parallel to each other?
No.
No. Okay. Can somebody else? I guess we are just talking one discussion. Can somebody else take out? Why there is you're not able to find any decision direction that is feasible also?
So why is that the professor says like it's in the opposite quadrant, sir? Like for delta f of x, the descent is below that line on the left side of the line. In this, as per this present diagram, the descent is for delta f of x is to the left of the line, and the feasible solution is to the right of the line.
Yeah. So the feasible
So
is this.
why is it in the opposite quadrant to what is the function?
So,
When it comes
okay.
vis-a-vis the function, why is it in the opposite quadrant?
Okay. So first thing, if you are having the gradient of f star in this direction, so please tell me what are the direction, like in which area you will get the dot product, or the direction with the dot product with the gradient will be negated. What are those areas for this effect, for delta effect? What are the areas where if you are doing the dot product with this vector, you will get negative values? Can you tell me which are the areas? So okay, for this, what are the descent direction? So like I'll just delete this.
Left side of the line.
So left side of the line. Okay, correct. So this is the descent direction. If I'm having this g x star, so now you're supposed to say this is the feasible direction, right? Correct.
Yes, yes.
Okay. So can you find any common between this? Anything common? Are you able to find anything common? Any direction that is common to both? Like, because you have to find one, even we are able to find one direction that is decent and that is feasible also. We'll directly say this is not our optimal solution. But if you are not able to find, we can directly say, okay, yeah, this is the optimal solution, because we don't have any direction where we'll move and the value is minimum from like value is less than from that whatever we are getting from it of extra. In this condition, we are not able to get any direction, right? Are you
Yes, sir.
following me?
Yes.
The third condition. If I don't have any direction, so then I can say that this is satisfying our second condition also. What was the second condition? Second condition was we should not be getting any decent direction that is feasible. So we are not able to get. So that means here whatever we were having the x star, that is satisfying our condition. And that if that is satisfying our condition, then x star is our solution for this optimization problem. Right?
Yes.
Till now, anything like, am I able to clear your doubt or anything else?
Yes, yes, sir. Actually, our motive is to prove that there is no lesser value than x that we can find.
Yeah,
If we can find a lesser value than x, then it is suboptimal. So
yeah,
in this present diagram, there you can't find a lesser value than x, because there is the intersection of the descent side and the feasible side is
nothing.
0. So the feasible side is exclusive to descent side. So so you can't find a lesser value than x. So x is the optimal value. Is that what we are trying to prove?
Yeah. But
So
in a different way, we are saying, like we are saying in which way we are saying. So whatever you are saying, like we have to get any values which are lesser than x star. Like at x star we were having some values for the function. Now we need to get some, if I'm the neighborhood of x star, if I'm able to get something, if I'm able to get some values which is lesser than f of x star, so we can directly say. So, but how we are saying, that direction in which we are moving, that is descent direction. Descent direction means when we were solving the problem gradient descent. So we were talking about the good direction and bad direction, right? So good direction is what? When we were having the delta, the dot product with direction to this, the dot product of direction, okay, and then the delta of x star should be less than 0, right? Why is that? Because we when we were applying that in that basic iteration, when we were solving with the help of gradient descent, then we saw that if I'm having, see, for example, like what was that? Like, can somebody tell me what was that? Okay, so if you have to solve the gradient descent problem, what are the equation in that? So simply that in that gradient descent we will solve if you need to get this value, right? So f of what n plus 1 was that fn plus some eta value, then d of del
Yeah,
f of
the
negative of this,
transpose that.
right? So we were what we were doing. We were just in each of the iterations we were just trying to go down and see that whether that is the minimum value or not. Right? So similarly, we are doing the same thing here, but here we were saying that this is the descent direction. If I'm able to get any descent direction, that means if I'm able to get in the neighborhood, if I'm able to get some values which are if we are getting some lesser values corresponding to the f the star, then we can say that this is the descent value I'm getting, descent direction I'm getting. That means x star is not the minimum value for sure, because there can be some other values other than that, other than x star, where we can get a minimum value than f of x star, right? So this is what descent direction we are talking about. Is this clear?
Yes, sir.
Yeah.
So we basically, it's almost like finding critical points, right? So we are looking for that point at which, beyond which both those conditions fail to exist.
Yeah, correct. So just we are finding some conditions, like we are finding whether the condition you can say or the direction you can say, where I'm just in the contradictory form. If I'm able to find that, then we can say that this is not correct, right? If I'm not able to find, then we can say this is correct. This is what we are doing, right? Okay, so I'll move further. Uh, okay. If so, this is what so if I'm having this the direction, if I'm able to get the word, if I'm this is the word, the decision direction, and this is the feasible direction, and there is nothing common in that, then we can say there is no direction. That is decent and feasible. So we are not able to get any direction. So the second constant is also applying. So we can say that here in this condition for our optimization problem, x star is the solution because this satisfying both our condition. So how generally we came to know about the Lagrange, like whatever he solved. So generally what happened? Okay, so from this condition we can say that one thing we can say, right? So the gradient descent of what is negative, like then the direction, the negative of what we can take some lambda value. Okay, so if both are anti-parallel, this we can conclude, right?
Yes.
And if they are parallel, but if they're parallel, the condition
Positive,
is
right? Lambda can be both.
yeah. So here, if they are if they are in the opposite direction, then what can be the value of lambda, whether it's a positive or anything?
If they're on opposite, lambda has to be positive.
So if the condition is this one, if they are both are anti-parallel, then lambda must be positive scale, right? Because if lambda is negative, then again the direction, both the direction will be like almost parallel to each other, and if they are parallel to each other, then we can get a large number of directions where the descent direction is visible also, right?
Yes.
Yeah. Okay.
Sir,
Yeah.
so why in the parallel case, if lambda can take either positive or negative value, why should we retain that negative symbol in the equation, sir? We can just call it as lambda delta of gradient. Because anyway,
Okay.
lambda is going to take positive or negative value. So why should we put a minus lambda? Like
Okay. So
minus
you can
symbol.
put it positive lambda, then you can say this could be negative.
No, anyway, we are going to put either positive or negative value for lambda. So why we need to still put a negative symbol
No.
before lambda is my question.
For this condition, you can't put negative value.
No, in this
If-
condition, positive we are going to put. So we can retain positive lambda only. Need not put a negative lambda. I mean,
Yeah. So this is what we are doing. Like for this case, we'll have lambda belongs to positive scalar value. But in the further cases, when we'll discuss, so this is for the inequality. Like if I'm solving the inequality, so constant with inequality, okay. Constant have any inequality, okay. When you solve the equation, the constant with some equality. Equality means gx was equals to 0, 1, some sort of like where the equality holds. In those cases, what happens if I'm having, like for example, this is the constant we were having, okay. In that case, what happens? If I'm having this was having the g, right? So this is would be the area. For the dc. Right. Now, if I'm having this constant g x star equals to 0, right? So I can have this direction, right?
It's the perpendicular.
Yeah. If we are having this, so in this case, the gradient, if I'm having, so here, this line, this direction, will be having the dot product. So the dot product, the direction with the dot product of direction with this gradient will be equals to 0, right? For this cases, if I'm having gradient, if I'm having gradient of g x star in this direction, okay. So this would be the line where the dot product will be 0, right? Is it clear?
Yes, yes, yes.
So this was the direction, and the descent direction was this one. So again, we don't have anything common, right? And in the same way, if I'm having, so here it was anti-parallel, but as it was holding this inequality, where g x was equal to 0, this was anti-parallel. This, in the similar way, we can take the parallel equations also. In the parallel also, because because we need to take this direction only, right? So now I'm having this as a, in a similar way, I'm having this f. In similar way, I'm having this g also. But here, because of the equality, that this is the line where the gradient of d dot, d means direction dot, the gradient of g x star will hold the equality, right? So this is our feasible direction. And the what are the descent direction? So the descent direction was this one. So again, there is nothing common. So we are not able to get any, because here we are able to satisfy the first condition also. The first condition is what? That the constant equation. The second condition, we are not able to get any descent direction that is feasible also. So for this case, we can write the lambda as anything. So we can write whatever. If we are like to write direct lambda also, you can write lambda also. If you want to write g star, anything you can write. So here lambda can take anything, any any arbitrary number or scalar. Okay. So in this case, so whatever you were saying for the inequality uh, like equation, inequality constant. So in those cases, you can't take lambda anything. If you are taking lambda, if you are taking the equation as gradient of f of x star equals to lambda gradient of g x star, then at that time the lambda should be negative. But in this case where the constant are in the form of equality, then this equation will hold. Okay, and this is also known as Lagrange multiplier. Like the lambda is known as the Lagrange multiplier. Okay, so till now it's clear. Like I guess.
Is this the same thing we used while doing the PCA thing, like doing the
Yeah.
derivation?
Yeah, we use the same concept to solve the equation there. At that time also we were having the equality. The constant was in the form of equal, like u transpose u equals to 1. So u transpose
Yes.
u minus 1 equals to 0. So that is the that was holding our equality, right? So that's
Yes.
why we have used this
For
concept there.
choosing the beta.
Yeah. Okay.
Sir,
So
can you give me some practical example where we apply this constrained optimization, sir? Finding the optimal value of particular thing.
okay. So I'll give you one
So,
simple question that has been discussed in the lecture also. Okay.
so can I suggest one thing? Whether is it right to this particular concept which we are explaining right now? Can I just suggest one thing, sir?
Yeah.
Like a company decides to price their product based on the expenditure. Expenditure can be three-dimensional vector, like x1, x1, x2, x3. X1 can be a marketing expenditure on that product. X2 can be raw materials, which expenditure which goes into making the product, and x3 can be something else, maybe packaging or something. So, but the price of the product should not exceed a certain price, because the customer acquisition will become costly. No customer will buy beyond a certain price.
Okay.
So it should be kept at a same 5 rupees packet, like biscuit packet 5 rupees. It should not exceed, but all these expenditure x1, x2, x3 in the three-dimensional, this is a three-dimensional vector space. So we have to find some three-dimensional point below which that there should be no there should be an optimal solution for this. In a three-dimensional space. So below which there should be no solution, no other solution. If there is a descent, so if there is a solution below that, that means a descent. So that means the current solution which you have got is suboptimal. Is this how I should understand?
Yeah. So this I guess this type of problem has been discussed last week also. So if you are having some like n vectors, like for example, whatever you told 3, or this can be 4 also, like the cost of transporting and all. So there can be some more vectors, or there can be some more variable, you can say, and then you can apply some sort of things like the summation of this, or the price of the product should not go beyond some value, and then you can apply some constant on all the equations, all the variable, like the price of the transportation, if you are like able to like transport it with the help of some roadways, then the price of this should be above, like the x3 or the x4, whatever you're applying should be greater than some fixed value, 5 rupees or 2 rupees or 1 rupees, whatever you're trying. So similarly you can apply for all the variables, right? Those are the constants that you're applying. Like for example, so if you have to solve the x1, x2, x3, x4, so you need to solve this equation. So for this you need to solve this equation, right? Your optimization problem is what? The summation, the price of the product, that means the whatever your cost, or the whatever you have told the variable 4 or 5 variables, the summation of this should be less than some rupees alpha, and all the values, and you need to solve this. You need to get what? You need to get some minimum x1, x2, x3, x4. That is what you are trying to solve, right? and then that should hold some other equations also. Like for example, you have some constant like x1 plus the transportation cost and raw product should be less than or should be greater than
Sir,
this
but
type of constant.
my question is, I didn't understand what is that g of x. Why only another one equation we are dealing with other than the main function, which is f of x? Why is another only additional one more function g of x we are dealing with? Why can't there be h of x?
Yeah,
Any other?
there can be some more like that you can represent in the form of matrix, right? If we are having more than one variable, or if, like for example, if you are having more than one constant, this is what you are saying, right? So that
No, sir.
constant can be more than one.
This I understood. I'm asking another question about g of x. We are talking of the main function for which we are finding an optimal value of x, which is f of x. Other than that, we are talking of only one other function, which is g of x. My question is, okay, for our level of
Yes,
grasping this concept, we are dealing with g of x only. But can there be
yeah,
more than more functions like g of x? Can there
yeah,
be h of x, z of x
this
more?
is what I'm saying. There can be more than one constant, like more conditions that you want to apply while solving the optimization problem. This is what you are asking, right?
No. Not with related to this vector, sir. X1, X2. I'm talking of
So
the g of x.
yeah, see, so this is the problem that has been discussed.
Can
Right?
there be multiple g of x, like h of x, g1 of x, g2 of x? Can there be multiple g of x?
Oh, so this is what we are saying. This is the this is the one condition that you need to apply while solving this equation. So there can there be any other equation?
Yeah,
Like
any other condition also, g2 of
yeah,
x
there can
on
be
the
any
same
other. Yeah,
function, on the same function.
yeah. For solving the, like for example, I'm solving one problem. I'm solving one problem like this the in the optimal like in the PC. Okay, then in the PC there was only one condition, but there can be more than one condition that I need to apply while solving the optimization problem. So there
That
can
will be
be
applied
more
on the
than.
given function. Okay,
Yeah,
okay,
there can be.
okay.
But here in whole courses in the MLF, we are just discussing about the only one condition. Okay, but there
Yeah,
can be more than one.
since we are just in the basic level trying to understand the
Yeah,
basic concept, we are just doing with only applying one condition g of x on the function given function f of x.
yeah, but there can be more than one. That's right.
Okay,
Sure.
thank you.
Okay. So the equation. So till now it's clear. Now I'm having one question, right? So this is the fx function. This is the optimization problem that I'm having. The optimization problem is this one. This is a question I'm taking from the lecture itself. Okay. And this is the optimization problem. So this is the objective. Okay. And this is the constant or the condition that you need to apply. Right. How will you solve this? You need to use the simple Lagrange only. So you need to use this basic formula only.
And use it for an equate for each.
This is x star, and x star will be in the form of 2 dimensions. How will you solve this?
So equate for each of the variables, like for
Yeah. So you'll apply. So you'll just find out the gradient with respect to a
yes,
function, right? So that will
and
be what.
so
So if we so this is simply the we have to differentiate with respect to x1, and this if you are having more than one variable, then you need to differentiate it. Like, so you'll get so if you are differentiating with this x1 with respect to x1 2x1 plus what 0, and if you are differentiating with respect to x2, you'll get 2 plus 8x2,
8x. Yes.
right?
Yes.
So similarly, if we'll calculate because you have to calculate the gradient of g function. So what would be that? Because you need to equate it, and then you get you'll be having more than two what equations, so you'll get the value of lambda, right? Now, what would be the gradient of g function? What is the g function? You'll get 2x1 and 2x2. Now we need to equate it both. So we were having 2x1 2 plus 8x2 equals to what? Minus lambda times 2x1 2x2, right? If we'll equate it, 2x1 equals to minus lambda 2x2. So from here, if you'll solve, you'll get either x1 equals to 0, right? Or what, lambda equals to minus 1 or 1, minus 1. So one equation, one solution. So now you're having x1 equals to 0. So now if you're having x1 equals to 0, you will get x2 also from here, because we were having that constant, right? That constant is satisfied, right? So you'll get some x2 also. So x2 will be what? If I'm having x1 square plus x2 square minus 1 equals to 0, if I'm putting x equals to 0, so x2 will be what? Plus minus 1. So you're having what? 0 comma minus 1 or 0 comma 1 as the x star. These are the two values you got. Now you'll get the values from here also. Now you're having the lambda also. So you can put the lambda here, right? In the second equation. In the second equation, you can put the lambda. You will be having 2 plus 8x2 equals to minus 1 times 2x2, right? So now you'll be having how much? So minus 2. Oh, sorry. So the lambda is minus 1, so minus into minus is plus. You will be having 2 equals to minus x2. So x2 equals to minus 1 by 3, right? So now you are having x2 equals to minus 1 by 3. You will put it here, x1 square plus x2 square minus 1 equals to 0. We put it here, we will be having x1 square plus 1 by 9 equals to 1. So x1 square equals to 1 minus 1 upon 9. That is 8 by 9 plus minus under root of this. So now you're having two values more. So x1 will be minus 1 by 3. So this is what we are getting. Minus 1 by 3, comma 8 by 9, or 1 by 3 minus 1 by 3 minus 8 by 9. So four values you are getting. Now you'll calculate the function value at all the four function values, and you'll get the minimum. So out of whichever is the minimum, you'll get the minimum or the x star. So corresponding to that minimum, whatever the x star you are having, that is going to solve our optimization problem. Okay. So for this equation, for this type of problem, it was pretty simple, and we were able to calculate with the help of Lagrange. Right? Till now, is there any problem? No, right? Shall I move further?
Yes, it is clear, sir.
Oh. I'll just delete this. Okay. So what was wanted to discuss? Just open the slide itself. So till now we have discussed. Now we are moving to this is what we have discussed, right? So should we solve the activity problem? Activity problems have you solved?
Yes, sir.
Was there any issue in that? Like somebody pointed out that there was some issue in any of the questions.
Yeah, one of the this thing was like, but I don't think it was exactly this one.
Which
Like,
question?
uh, like there was an issue with like one of the issues I saw uh, on this one on discourse was the thing with
To the
the
webinar, you have entered as an attendee in listen-only mode.
like there was an issue with the local minima, but that is about the convex functions and things like that.
Okay. Okay, that question.
Like there was a question about like whether
Yeah, this
local
is
min.
which of the following is true about the convex function, right?
Yeah, exactly that.
Okay. So what do you think? Which one is correct?
I think that the value of the local, like there should be only one local minima, but then when you go to higher dimensions, the thing comes where like if it is indefinite,
What
right?
about this
So
function? Hmm. This is having only one minima, right?
yes,
Okay,
that
this
is
is
the hint.
convex also. What about this
Yes,
function?
it is flat at the bottom.
Okay, this is flat.
Yeah,
This is convex, right? But there is like there can be more than one minima, right? But
yes,
that should be same. The value should be same.
yeah. Then there was this issue with one of the lectures, but then I think it was later clarified by another student as well. It was just a mistake in the way he told like, about the Lagrange multiplier.
This one.
Like not in the question, like in one of the lectures, like towards the end, sir just like mentions that the lambda should be 0 for I think for for the in the case of equality related one of the cases.
Okay.
I think, but I had put it on Discord. It was later clarified like by another student.
The discourse. Okay, this was the question, I guess, that we have
It is
discussed.
8 AQ 8.5.
8.5.
Last question.
Which of the following are function for which the local minima is same as global? Okay. Which of the following is function for which local minimum is same as global minimum? So that function should be convex. Okay. Okay, the first is a square, then first is correct, second is also correct. So I guess all the answers are correct, right? Sine generally, if I'm applying some, what you can say, limit on the sine function, then it can be possible. Local minimum can be the global minimum. But if I'm taking the sine function as overall, what happens generally? It's a periodic function with 2 pi, I guess, or pi, 2 pi. So the function values will be minima, okay, but that should be a unique for the global minima. It should be a unique value x, okay. So if that is not unique, this can't be a global minima. Did you get the point? Like it's the value is minimum, like but many of the books will tell this is a global minima also. But for the global minima, one condition should be satisfied that the x should be unique. Okay, because if you are having functions, and the global minima is repeating after 2 pi, right? In this, like in the sine case, it's happening because the global minima, or you can say the local minima. If I'm applying some conditions, like for example, from 0 to 2 pi, then local minima is the global minima. But if I'm not applying anything on the domain, then it can't be, because we are getting the global minima at many a times, like in the 2 pi k we are getting, like whatever the value sign, generally minima is there. So this is what 3 pi upon 2, or what, this pi, so pi plus 5, yeah, so 3 pi, so you are getting 3 pi upon pi k. So, so this is not minima because it's repeating after every 2 pi interval. And after because the global minima is, to get a global minima, that x should be a unique value. That's why here it has not been referred as global minima for this case. But if you have been asked to sin x and that x belongs to 0 to 2 pi, then this is correct.
Okay, thank you.
So,
Yeah.
just to add on, in continuation with this, the
Yeah.
difference between this and the example we just saw in the case of it having only one, like it can have multiple global minima, right? In the case of convex. So clearly, like sine function is not a convex function, right? But the difference over there is the presence of a local maxima in between.
What difference is that in this function?
Is that, yeah, like since there is an ascent in between two like descents, like if you can say it that way.
I didn't got the
Because like in the second graph you drew, like over there too, like
here the
there
x is unique. Like x is unique means the values are same for all the.
No, that x
Not
is
the
not
function,
unique, right?
not x is not unique. The function is same for all the x, whatever I'm taking.
Okay, yeah, yeah. So like it is okay. So they are different things. Okay. Yeah, I had a slight confusion with it.
So anything else from last week, or so this week you have not solved? Okay, but fine. So we have discussed till 9.3. I'll just start with 9.4. So 9.4 is basically the gradient. What is that? Gradient descent? No, sorry. Convex or what? Convex sets.
Yeah, convexity. So in 9.3 there is one more portion. Like towards the end, he mentions about this thing, the projected gradient descent. Like some phi of the gradient descent itself, but the pi of gradient descent.
Okay.
So, like he just mentions it there, and like I have not really seen it anywhere else in the main lectures.
So in the okay, this one projected gradient descent, right?
Yeah.
Okay. So in this case, what he has discussed, like if I'm having this is the constant, right? This is the constant, right? But I can get the gradient in some different direction that is not in the direction of the grade, like the constant, right? So what we can do is, if I'm having some constant and the gradient or the descent direction or the gradient direction was very much like the x, like we have started with x naught, okay, to solve the gradient descent. So he's just trying to say, see whether we can apply that Lagrange every time or not. So Lagrange we can't apply every time, right? Because there can be some other, like there can be that somebody saying the optimization issue, like the constant issue can come every time that inequality will not hold, right? So inequality, there can be some problem where inequality is there. So every time the constant is not that simple, that we are able to solve with the help of Lagrange multiplier. So, but there can be issue, right? Constant is like here the gx is less than equals to 0, less than equals to 0. But we can have that if I have initialized the x naught, so that this formula is there that we generally use in a gradient descent also. The same concept we are applying here, but what we are trying to do, whenever this direction, whenever this direction, that means whenever this losing or this getting in different direction apart from this constant set we are having, that constant set we were having, right? So gx less than equals to some sort of s,
Yeah,
you can say, or like, so if this not in the same direction, then what we'll try to do, we'll try to get the projected value in the same S set or the constant set, so that it will come down. It will be helpful for us to solve with the help of so what we are doing, we are just applying some conditions on the condition, like then the projected in the gradient descent. Now I've started applying some basic relation, or not the function in that pi function we have started applying. That what is that pi function? Pi function is such that pi is generally the constant, or this is okay, that this set of the values or the function where the constant can be applicable. Okay, so we are just, whenever there is this losing the direction, so we are just trying pulling out in the direction, or in the set where in the basket of sets, okay, where it will apply, where it will the constant things will get applied. Okay, this is what generally we are trying to do in the projected gradient descent. Okay, so we are just applying a function in, like whatever the gradient descent we were having, we were applying a function, and that function is what the projected value of those cases. Like if I'm trying to go from xt to some next value, like we are generally increasing in in each of the steps, we were just adding some step or subtracting some eta value with the gradient value. So now we are taking the projection of that, and the projection should should satisfy this condition. So this is the condition that we are applying in that, like while coding or whatever we are doing in the projected gradient descent, we are applying this condition to satisfy, so that it will come under our basket. This is what generally we are doing to solve the problem if we are not able to solve with a Lagrange multiplier.
so in this case, like when we get the optimum value, like since they will be like anti-parallel, there won't be any correction. So till we get to that level, so when we get that level, that pi of x would basically be 0, is it?
Okay, what you again, can you repeat that?
So like if we have like a case where they are anti-parallel, right? Like that is when we get the optimum value.
Mm-hmm.
Right. So when we come in that case, like when we project it, right, onto the y, so that will basically be the gfx star.
Okay, yeah.
And in that case, the projection, like it would be what? The projection would be 0, is it?
Yeah, correct.
So but even
The projection, see, like for example, here I'm moving from x. This was the point, like initialized point, starting point. So we are moving in this direction, but this direction is not in our constant like basket, right? So
Yeah,
what we
yeah.
are just pulling out that direction to such that come in this, like this. Now after that projection value, this generally comes under our feasible state or feasible direction, whatever you trying, whatever you
Yeah, yeah.
want to say. Okay, so that's why we are just projecting those values so that it will come under our basket, and it will come under a basket. That means it's applying like the constant thing, whatever we are trying to put on the optimization problem, that is getting satisfied now. Okay, so this is what we are doing in the projection basically.
Okay, so we just okay.
Okay, and this
Wait, this.
yeah, this is generally, so you can, this is generally talked in very brief. Okay, so like I'm also not much aware of this concept, projected gradient descent, because we have like I have also not used this concept. So maybe we can refer, like I'll refer some more blocks and all, then we can discuss it more. But you can also try to go through some blocks. And is it fine?
Yes, sir. Yes.
So the next topic is the convex state. So apart from you, nobody is speaking anything, I guess. So just simply okay. So should I discuss more or what? Should I discuss it in the next session on the Saturday, or what should I do? Because nobody has seen, nobody is speaking out also. One like so monotonous, like I'm just speaking out, nobody else is replying. So what should we do?
So during the next sessions, like we would be focusing more on the quiz. Right?
Yeah,
We got like around 10 or 11 days or something.
yes, I'll just go through in a brief like convex set, and then I'll just discuss. There is not much left now, right? So convex
Yeah.
set and then convex function. That's it. So introduction to the convexity. The convex set is simply like it has been defined beautifully in the lecture. Like if I'm having a set S that is belongs to some real value, and that real value can be in the D dimension also. It's a convex set. If for all x1, x2 that belongs to it, then it should satisfy this condition. That's it. S belongs to R. That can be a D dimension also. Is a convex set. It's convex if for all x, whatever I'm having, x1, x2, or belongs to x. For all lambda belongs to 0, 1. Okay. So a convex set S generally belongs to R of D dimension. If for all x1, x2 belongs to x, then this will also belongs to x. This if x1, x2 is belonging to some convex set S, then this value, or you can say whatever the x bar, lambda x1 plus 1 minus lambda x2 will also belongs to the convex set. Okay, and the lambda will vary from 0 to 1. Like for example, we are having some x1 here and x2 here. So this line, you can say, is a set of all values from x1 to x2 is a convex set. Because so if you put lambda, the minimum value what the lambda can take is 0. If you put the lambda equals to 0, you'll be having x2. And if you put lambda equals to 1, you'll be x1. And you can get all the values in the combination of x1 and x2. If you'll take lambda with some wiser values, you'll be able to know, if you will be able to get all the set of values from x1 to x2, right? So this straight line, or you can say the line from x1 to x2, or the set or the values from x1 to x2 is simply a convex set. Because why? Because it's satisfying this condition. Lambda x1 plus 1 minus lambda x2 for all x. Like if x1 and x2 belongs to S is a convex set, then this values will also belongs to the convex set, where the lambda will vary from 0 to 1. So this was pretty simple. I'm having x1 next to that is belong to some convex set. Then all the values lying from this line from this here to here will be a convex set, like will be under convex set, because this satisfying our conditions that lambda x1 plus 1 minus lambda x2 and lambda is from 0 to 1. That we have seen, if we'll put lambda equals to the minimum or the lambda equals to maximum, we'll get some x1 to x2. Like for example, if I'll put lambda equals to some other values, 0.2, we'll get some values here. Okay, that is also under convexity, right? Yeah. So, or you can say in the lecture it has been talked, like if you are having some in the number system, like for example, this is from A to B. This is a convex state because you can get any values in the combination of this number, right? Like for example, here it is 9, and tell me whether this is a convex state or not. So A B union C D,
No,
right? Why?
there are points between B and C which cannot be expressed.
No, it can't be expressed in those forms, right?
Yeah.
And simply how generally we define, like how generally we write in this, like convex with the plot, if you see that, like for example, this is a plot. Okay. If you are taking some two values, like for example, this x1, this is x2, right? So if I'm taking x1, x2, or like for example, if you are able to plot this like this x1, x2, one second. Okay. So okay, so can somebody, if this is a set of all the values, is this a convex set?
Yes.
And tell me, this is a convex set or not?
No,
Right? Why?
because there are points between the left and the ear,
Yeah.
left and the right side which comes outside.
Yeah. So we can plot this line. There, this values are not coming under our set, right?
Yes.
And this can be written in the form of x1 plus x2, like x1 and x2. That's why this is not a convex. What else has been discussed? Okay. So this is a basic example. There can be something. So convex set generally. So if you are having some set S1 and if you are having some set S2 as a convex set, so always one of the important properties that the intersection of both the sets will always be the convex set, right? So the intersection, like for example, x1, you already know this is a convex set, and S2 is also convex set. The intersection will always, the S1 intersection S2 will also be a convex set, right? Can it be true for S1 union S2?
If there is an intersection, yes. Otherwise, we can. I mean, it depends. Right? If it is,
See, for this example, if I'll take the union, this was not satisfying, right? Because we can get with there, this values are not on the convex set, but this, right?
yes.
If I'm having some this, like for example, this is the S1 and that was from A to B. This is the convex set, and this is the C to D. So the intersection will not be, sorry, intersection. In this case, so intersection will also, if you're not getting anything in the intersection, then
Yeah.
right? But in the union, if you are having some convex set x1 and convex set x2, right? So the union in the union not compulsorily will be a convex set, right?
Yes.
Like for example, similar thing was there for the hyperplane also. If you are having some hyperplane x such that W transpose x equals to B, so this is a hyperplane we are having. Okay, W transpose x equals to B. Okay. So if you are having this hyperplane, so any hyperplane can be a convex set or not?
Yes, it can. It
Right?
will
Because
be.
yeah, because if f1 belongs to S and x2 belongs to S,
Yeah.
that means it is satisfying this, and it's also satisfying this x2 equals to B, right? Then you can write in this form W transpose of this. You can write lambda x1 plus 1 minus lambda x2 equals to B, right? And if you just open it, x transpose x1, and this is B lambda times B1 plus, what is that? Lambda transpose 1 minus lambda x2. This also you can write 1 minus EQ. How will you write this? I guess you're doing some mistake or what?
Yeah, I think this is exactly that will be lambda times wx1.
So this can be written 1 minus lambda,
W transpose.
1 minus lambda times W transpose x2, and this is equals to B, right? So this lambda, B and lambda will get cancelled and we'll get B. So this is satisfying our conditions to get the convex set, right?
Yes.
So the basic properties, what was discussed in the lecture was if you are having some complex shape, convex shape, and this is the x2 is the convex shape, the intersection will be a convex shape compulsorily. Okay. Okay. So what is this convex function? What is this convex function?
Yes.
And what is concave function?
Q was not.
So there can be the convex function, there can be, so one basic, okay, so convex function can be represented in this way, right? The concave function can be represented in this way. So there, so see, whenever we are solving the optimization problem in most of the cases that we have discussed, like this minimum cases can be converted to the maximum cases also, right?
Yeah.
Because we can write in the form of, like, if somebody would have read about the SVM, in SVM generally what we do in SVM or some other algorithm generally, whenever you have to calculate, if you are able to, if you have to calculate the maximum of some x, some optimization problem is there, then you can convert that in minimum 1 upon this condition, right? That can be the one method that you can solve the optimization problem this way also. Okay. So how we generally will define convex function?
Convex is like the function should have like the set should be from a convex set, right? The domain should be convex.
Yeah, so only that, but that is not the compulsory part. Like if we are having the function from RD to RD, if this having the domain as convex set, if this is not a convex set, then this is pakka, this is not a convex function. But if this is a convex set, then this function can be or can not be. It can be
Yeah, yeah.
and it can't be also. But if this is, if whatever the domain we are putting here, if this is not a convex set, then for sure this is not a convex function. Okay, this is the first condition. If you are not, if the domain is not the convex set, then it's not a convex function. But if you are putting the convex set, the domain, this can be or this cannot be. Okay. So what has been taught in the lecture? So there are some 2-3 methods that you can use
Yeah.
to know, right?
Yeah. The graph.
So the first is the epigraph. So a function that is f RD from R, where the R is the domain is the convex state. It is a convex function if whatever the epigraph you are plotting is a convex state, right? And what is this epigraph? So the epigraph of function is what? So if, like, for example, this is the function you are having. So what is the epigraph of this function?
The portion above the graph.
Yeah. So this is the portion above. How do you define the epigraph? The EP graph can be defined. Generally, EP graph is generally in the form of R plus one dimension. And where R plus one dimension, like for example, XY, and such that it belongs to D plus one. And where the Y is greater than function of X. Right? So that means, like for example, this is X1. So here it was, the function is this fx1 greater than fx1. Similarly, you can take all the values. So whatever the values which are greater than this function, okay? So this is satisfying this condition. This condition satisfied means what? This is the whole area. This is the whole set. That is the convex. Right? And this is the EP graph. And this EP graph is a convex set. Right? That we already know. Okay, this is the one method to describe the convex function. There can be other method also. The second method is, I don't know whether this lecture is useful or not because nobody is responding anything. So the other definition can be, like for example, what are the other definition that has been talked in this lecture? So the
We have
differentiable.
the Hermitian,
So,
the
yeah, so-
Hessian, not the Hermitian, the Hessian.
okay, from the Hermitian also you can directly say, right? If you're having, like for example, yeah, if you are able to calculate the Hermitian, whatever you are having, df of dx, right? And this Hermitian matrix that you are calculating. So this we have already talked. This Hermitian matrix should be positive semi-definite, or I guess positive definite also is there. Then this matrix is all positive definite. Then this matrix, then the equation is a convex function. These are pretty simple. Like for example, if you are having some x square. So x square means what? You are having only 1 cross 1 matrix, right? If you will calculate the Hermitian matrix or what?
X square then would be a Hessian matrix should be like just one, right? No, two. Yeah, two.
So 2, then 2 is positive, so you can directly set the convex function with x square. So this is the second method. There are the other method also, like with
Yeah,
this function differentiable
linear
method.
approximation.
This f of y should be greater than equals to f of x plus y minus x. For transpose, if you are able to write this. So from where we are getting, if we are able to plot this function, this is a function, for example, right? If you are having this function, this is x, equal this is y, right? So if we'll plot the tangent, what is this? This f of y should be greater than equals to f of y plus y minus x ka transpose into del of fx. So del of fx, this one, right? Sorry, this is the plot, right? Okay, so this is y minus x. This is what? This f of x. This was f of x, right? So this is f of x, and this will be what? Say for example, this is k. So I'm just telling you from where we are getting this equation. So k can be theta. So what is tan theta? Tan theta, how generally write? Perpendicular plus hypotenuse,
A
right?
perpendicular by horizontal.
Sorry, base.
Yeah.
Base, right? So what is the perpendicular? This is the k. This is the k. What is the base here? The base is y minus x, right?
Yes.
So you can write this. You can write this k as what? And tan theta is what? Del of x.
Greater than.
Del of x
Greater than.
into y minus x. So this is what k. So then directly you got this equation. So this x. We got this equation. This is f of x plus this k. So f of x plus k. So f of y is greater than equals to f of x plus this value k, and this k is what? Del of f x of y minus x. And if this is in the more, like the dimension is the more, then you can directly write the transpose of this y minus x. So this is how we are getting this equation. This is also the one method to show how the function is a convex function. Convex function. There are other methods also, but I get yeah.
We substitute the function instead of uh, the linear approximation.
Yeah, that also is a one method. That is also convex to show the function. If x1 and x2 belongs to R, then for all lambda that is from 0 to 1, that function at x3 will be less than equals to function of if lambda into f of x plus 1 minus lambda f of x2. This is what you are saying, right?
Yes.
So like for example, this is a function I'm having. This is the x I'm having. The x2 I'm having, right? This is the x3. Right, so this is the x3. So we are having fx1 here. This is fx2. So if this is what x3, we can write it as like this: x3 equals to lambda x1 plus 1 minus lambda x2. So f of this function is how much? This, and this function is less than equals to this one, right? This can be written as lambda fx1. Have you got the point? Because see, x1 is this one and x2 is this one. So fx1 is this one and fx2 is this one. If you'll apply this condition, lambda into fx1 plus 1 minus lambda into fx2, we'll get this value, right? On the straight line, if you're having this fx1, fx2, you'll get this value. But from here, if you are applying directly this value in the function, if I'm applying this directly in the function, you'll get this value, right? This less than equals to this. So if this is how it's happening, then you can directly fix the convex function. There are 3-4 methods that you can use to prove that this is a convex function.
In general, can we say that
the most simple way is the Hessian matrix, you can say, or even if you're having the plot, then you can say that this is a convex function. If you're having the plot, yeah. What are you asking?
Yeah, so if we can say that there is no global maxima, defined global maxima or something, can we say that it will? Can we say
if you know, if you are having convex function, then your local minima is itself the global minima. So there won't be any other. If you are having, see, that we have already discussed in the starting also, if you are having the function which are having multiple local minima means this type of functions, right? For this type of function, we can't even use our gradient descent method also. And this is not the convex like function also, right? If we are having multiple local minima and that
that's what I was. But then I was thinking that if you don't have a maxima, then we can. But then if you take the case of circles, that won't be satisfied. I think there will be a global maxima for that as well.
Yeah.
I was just thinking. But,
the problem is I don't think so today's lecture is helpful for most of you because you have not seen the lecture, right? So, like, can somebody or please suggest what should we do? Like, not today, like, and now we'll be having one more session. Like, we can have more sessions also, but first you need to pass the lectures, right? I guess in spite of me and Legon, others are sleeping, I guess, or they're not picking up. Like, what should we do? Whether we will have the session solve with us session on Saturday or not, or what
So
we want on that
maybe
Saturday.
like after today's session, maybe
Yes,
watching the
we should have
lectures
on
like
Saturday one more session.
What? Harshal?
Yeah, we should have a session on Saturday. Solve with us.
Okay, we'll have that session. Okay, on the Saturday we'll have that
Saturday,
session.
Saturday normally it will be solved with instructor, no?
Yeah.
yeah.
So that is necessary actually because Sunday will be the graded assignment deadline. So
I think by that time, like watch the.
sorry.
I think by that time, like since we have a general idea now, by that time, like people can watch the lectures. I think.
Right.
Yeah, so by the time you can watch the lectures, and if you are having any issue, we can discuss on the Saturday, and the rest of the time we'll wait for the solve with us. We can discuss the activity practice also. So you're having 3-4 days, you can solve also. Activities are pretty simple, right? So those you can just watch the lecture and go. Practice you can just solve. While solving the practice assignment itself, you'll solve the graded. So if you're able to solve by that time, by Saturday, we'll discuss like half of the time, and then we can give the half an time for the solve test, or maybe we can extend the session because today we are still closed by now. Okay. And for the revision session, I guess you are having the revision session on the next Wednesday. And any extra session if you want, you can have. Like the mock will be released tomorrow, I guess, or day after tomorrow, maybe on the Friday. And that also, if you want, we can discuss on the next week session. It is totally conceptual. You can just watch the lectures once or twice, and maybe it will clarify your doubt, or we'll discuss on the Saturday.
So what will be the syllabus? Like it is till week 8 or week 9?
From 5 to 8 only. I already told you in the starting. I explained you also what you have to write, what you have to solve, so that you can.
Oh, sorry. I could not attend the starting. I joined in mid.
Yeah, so
I can watch it on YouTube. Right?
Yeah. So 5th to 8th week, and I told you the important topics from those. What you have to solve, what you have to solve mostly.
Yeah. Sure. Thank you.
Oh, okay then. So in the discourse also, most of the doubt I guess we have discussed, and so we don't have anything.
Sir, one small doubt.
Yeah.
That is in a single dimension. If f of x, select if f of x is like not a polynomial, it's a single like monomial. Then you can say like something. The x value is less than a certain thing. Like if x, I mean, but in a two-dimension, like how do you say it's less than? Like how do you determine the lesser value for x in a two-dimensional or three-dimensional? It is only within the neighborhood you can maximum say. You can maximum say like the optimal value is within the neighborhood of the x. But you can't just exactly say like there's a lower value when it goes to three-dimensional plane. In a three-dimensional plane, there is no lower value, no, sir. Like lesser value to it of a function x. It's only within the neighborhood.
Like for example, you're having some 3D picture.
Yeah, 3D picture which has
3D
x1,
is simply
x2,
a
x3,
plane, right?
3 coordinates.
Okay, this is a plane. This is in the 3D, right? So this is simply, you can say, a bed sheet. This is a bed sheet, but there will be some minimum value, right? The bed sheet, if you are just putting like two people are holding the bed sheet in this, and two people are holding the bed sheet like here and here. Okay, and not totally tight. Just we are living. So there will be some portion where there will be some minimum value, right? for some plane, like this plane or some sort of thing.
Okay, with respect to that first part of this session where we touched upon that optimization, like minimum value of a function f of x we are determining. If it has some, it's a three-dimensional. If that f of x is of a three-dimensional nature, like which has comprises of x1, three variables x1, x2, x3.
So we discussed for
that
the
kind
two
of-
dimension,
so-
right?
So in that
like,
case, like minimum value means like you can't determine something in a three-dimensional. If you plot that x function f of x, which has which is based on three variables.
Yeah,
If you
so
plot that,
you need to check the neighborhood of x1, x2, x3.
can you can you certainly say like there's some minimum values? Can you use that term, or is it only within the neighborhood we can see?
No, so there will be some minimum value, right? For example, this is the x star, and x star is simply x1, x2, x3. And for this x1, x2, x3, whatever the plane I'm having, this plane that is in the three-dimensional or n dimension. Okay, so some, like for example, this is the n dimension. So there will be some x value that is in the n dimension where the value would be minima for irrespective. Like for example, this is a 3D you are saying. So like for example, I just moved in x1 direction. Now x2 and x3 I fixed. Like for example, x2 and x3. I moved in x1 plus d delta. Now I check the function value at x1 plus delta. So there will be some function value at x1 comma x2 plus comma x3, right?
Yes.
Okay.
Which will be
So
minimum.
Yeah. So like for example, x star was a minima. Now I check for the x1 plus delta. I fixed the two thing. I just moved in x1 direction, and then I moved in the other direction. I moved in the third direction also.
If there are more than one minimum value, if you can determine more than one minimum value for f of x, then it will be like, it will not be a global minima, it will be like local minima.
There will be only one minimum value, right? There can't be three minimum values.
No, see, instead of keeping a x2, x3 constant, like you have a x1, you fix
no,
the x1
this is
and
I just moved
vary
this.
the other
I just like for example, if I just fixed x2 and x3, and I just moved x1 plus d in any direction, right? If I just move in any direction, and if I am able to find that, see that at x star, and x star was what, x1, x2, x3 for me, and for this corresponding f star, so don't think that as a three-dimensional, four-dimensional. F star, there will be some value, k value, right? And if I'm able to put if I'm able to put in this function itself x1 plus delta and x1, x2 and x3, and if I'm getting some k minus a small k, so this would be my next minima, right? This is the minima for me now. And if I'm able to move in neighborhood of x2 and x3 also, if I'm able to get some lower value than this f star, then I can say that I'm able to find some other minima also, right?
So those are local minima, sir. If you can find.
Yeah. These are all we are talking about the local only. We are not talking about anything global and all. We're just talking about the local.
Finally, for the function, you can determine one global minima for sure. One function can have one global minima for sure. In any direction, maybe for in x1 direction or x2 direction.
For the function which are ever we are talking, we are just talking about the convex function. And the convex function, for the convex function, the local minima is the global minima. And if you are having a function which are having more than one local minima, okay, for those functions we are not solving with the help of this optimization with whatever we have discussed till now. So for those cases, I don't think so there is an algorithm how to solve that. Like for example, like you are telling, this is a 3D picture, 3D some plot. This can be some 3D plot, right? We are having some more than 2-3 minima, right? So if we are able to strict the set, then we will be able to know regarding this minima. If we are not able to strict this values or domain, then we will not be able to know regarding the minima of this cases where we are having more than one minima or more than one maxima.
We can't. If we have more than one minima, we can't represent the entire picture with some
we can't
lower matrix.
We can represent. We will not be able to solve that problem.
We can't exactly represent the entire picture in the form of one small equation or a matrix.
Will not be able to solve that if we are having more than one minima in that function. And even all the best algorithms that we are using, most of the algorithms we are using just for the convex functions. Anything else? Anything else from anyone? Anything else? Lee, John, do you have any questions or should we close it?
No, sir, I don't have any doubts yet.
Okay. So anything else? No one is speaking out. Okay, then I'll just close the session.
Yes, sir. Thank you, sir. Thank you, sir.
Oh, okay. Thank you. Thank you,
Thank you.
everyone. Yeah. Thank you.
Thank you.
Thank you, sir.
Oh, thank you.